Hello, everybody. Welcome to our first lesson. Today we're going to be talking a little bit about the metric system, metric conversions, and scientific notation. Right. So what we're going to start with today is the metric system itself, and talking about measurements in chemistry. Right. This whole year, everything we talk about is going to be done using the metric system because, first of all, it's the scientific standard, and second of all, it's better and easier than the American system. Right? If we're thinking about the American system of measurement and we want to talk about how long something is, we can use inches, right? There's 12 inches. We could use feet. We can use 3 feet equal 1 yard. We can use 5,280 feet in a mile. Right. These units, inches, feet, yards, and miles, are only used for length. When we think about volume, we want to talk about how much liquid there is, we talk about ounces, cups, quarts, gallons. Right? A different set of units, a different set of numbers in between them. I honestly don't even know how many cups there are in a quart, how many quarts there are in a gallon. Right? It's a different set of units entirely. Whereas in the metric system, when we go and we want to look at metric units and metric conversions, it's always changed in multiples of 10. We have prefixes that are going to be the same across the board, and the unit is going to follow after the fact. So for example, if I have a centimeter, I know how big a centimeter is in relation to a meter because of the prefix in front. And the same thing goes with a centiliter. The prefix tells me the scale of my measurement, and the suffix, right, the unit itself, tells me what thing I'm measuring. Right, a centimeter is a small unit of length. A centiliter is a small unit of volume. I can do the same thing down the line. I can say a centilumen, a centibyte, a centidecibel, a centijoule. Right, all of these things are going to tell me a small amount of whatever thing we're measuring. Changing the prefix is going to change the scale of that unit, right? A kilogram is much bigger than a milligram, right? And a kilo means 1,000 of whatever we're measuring, no matter what the unit is that we put after the fact. We're going to take a closer look at metric units and metric conversions in a second, but first we want to take a small detour over to scientific notation. With scientific notation, the whole point is to take a big and unruly number and put it into a number that's a little bit easier to visualize or to see with your eyes. When we take a big number, right, a number that is much bigger than 1, and we put it into scientific notation, we are going to take our decimal and we're going to move it some number of places to the left. Right, 1, 2, 3, 4, 5, 6, 7, 8 places. And we're going to end up with a new scientific notation number, which is going to be 1 times 10 to the 8th. So when we have a big number, a number bigger than 1, we move the decimal to the left and we have a positive exponent. If we have a small number, a number much less than 1, I'm going to move up here for this. We're going to have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 3, 6. When I want to put this number into scientific notation, again, I'm going to take my decimal and I'm going to move it some places this time to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. And I'm going to end up with a new number, and that new number is 3.6 times 10 to the negative 11. Right? When we have a small number, or a number much smaller than 1, we're going to move the decimal place to the right, and we're going to have a negative exponent as our value. Something else to remember as we are thinking about and looking at numbers in scientific notation, your goal is to get a single-digit number before the multiplication sign. Right? 3.6 is a single-digit number. 1 is a single-digit number. What we do not want is anything more or less than a 2-digit number, right? 10.3, that's bad. We don't want that. 0.103, also bad, right? We want a single-digit number, right? So something between 1 and 10. Right? We do not want a 2, a 3, or even, right, a decimal point before the multiplication sign. We would like a single-digit number there. When you have numbers in scientific notation, right, for example, if this was my number, I'm not going to round this number. Right? A number in scientific notation should not be rounded unless it is a particularly large number, right? So, for example, if I had this number, this is a number that I might want to round because this doesn't actually save me anything by being in scientific notation. Right? The fact that this is times 10 to the 6th doesn't really help me because it's still so many numbers. So here I would round to 3.68 times 10 to the positive 6. Right? Again, the whole point of scientific notation is making a number that's a little bit easier on the eyes, a number that's a little bit easier to understand and to see. Now, jumping back to our metric system, right now that we understand a little bit more about scientific notation, we're going to take a peek at our metric prefixes. Like I said before, we have prefixes that is then going to be followed by a unit. And like I said before, again, the prefix means the same thing no matter what unit we are looking at. Right, so if I have a nanometer or a nanoliter or a nanobyte or a nanojoule, all of those units are going to be to the same scale, right? They're all millionth. They're all a billionth of the regular base unit. And so here I've put little purple dashes, right? Because these are universally used, right? I can put whatever I want behind these prefixes to show the scale that I want to use. And so no matter what, a centi something, right? Centimeter, centiliter, is always going to be 100th of the base unit. A milli something is always going to be 1,000th of the base unit. And as you continue down, you get smaller and smaller and smaller numbers. As you go up, you get bigger and bigger and bigger numbers. Right? Think about something that most people use every day, right? You have megabytes, kilobytes, gigabytes, terabytes down here. Right? And you see that they get bigger and bigger and bigger. If you're going to convert between different metric units, you want to keep these in mind, right? The important ones for us are going to be these 1, 2, 3, 4, 5 up here. Right? These are the ones that you're going to see used the most often. These are also on your reference table for you to look at any time on table C. If I said I have 20 centimeters and I want to know how many meters that is, I have the number that I need to convert from centimeters to meters. I know that 1 centimeter is 0.01 meters. A centimeter is smaller than a meter by 2 decimal places. So I want to make this smaller by 2 decimal places, leaving me with 0.2 meters as my conversion there. If I have 100 kilograms and I want to convert that into grams, I know that there is 1 kilogram for every 1,000 grams. It's 3 decimal places bigger. So I want to take this decimal place and move it 3 places bigger. So I'm going to get 100,000 grams. What we're going to take a look at now are some practice problems. We're going to mix in some scientific notation with some metric conversions. For these, you do not have to put an answer in the chat. You should try to get an answer on your own. I'm going to wait about 10 to 12 seconds before going over an answer. So if you need a little bit more time than that, you can pause the video and then resume it whenever you'd like. For this one, I want to put this number into scientific notation, which means I want to take this decimal and move it over to condense my number down and get something times 10 to the something. All right, I'm going to move this decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places. So I'm going to get 1.47 times 10 to the positive 12th. I took a big number and I put it into scientific notation, so I'm going to have a positive exponent. All right, which gives me choice 1 as my answer. I know for a fact, even before putting this number into scientific notation, that choice 2 and choice 3 are bad choices because they do not start with a single-digit number. Right? A correct scientific notation has a single-digit number in the front. Right? 147, not a single-digit number. 14.7, not a single-digit number. 1.47 is a single-digit number, so that makes it a good candidate, and then on top of that, it's got the right exponent in the back. For our next practice problem, we're going to take a conversion. 170 grams is going to be equal to how many kilograms? You know that 1,000 grams is equal to 1 kilogram, because 1,000 whatevers is always equal to 1 kilo whatever. So I'm going to wait about 10 seconds, So if I want to solve this problem, I'm going to say there's 170 grams in how many kilograms? I know that kilograms are bigger than grams, right? I know that there's 1,000 grams in 1 kilogram, so there's two different ways I can do this. I can look at this and make my ratio and do a conversion that way. 170 grams times a kilogram over 1,000 grams. Have those cancel out. End up dividing by 1,000 for 0.17 kilograms. Or, alternatively, I can say I know that a kilo is 1,000 times bigger, so that means this number should get 1,000 times smaller. So I'm going to move the decimal place 3 places to make this number smaller, again giving me 0.17. All right, no matter how you end up slicing this, whether you're making a ratio and solving it this way, whether you are knowing that a kilo is 1,000 times bigger, so that this should be 1,000 times smaller, right? No matter how you slice it, you get 0.17. For our next one, it's going to be another scientific notation question. Again, if you need more time, please pause the video and then resume it. I'm going to give you about 10 seconds here. Alright, so here when I'm trying to put this number into scientific notation, again I want to move this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. When I move this decimal point 10 places, I'm going to get 3 times 10 to the negative 10, because I took a number that was smaller than 1 and put it into scientific notation. I'm going to get a negative exponent, which is going to end up being this choice 3 here. Right? 3 times 10 to the positive 10 would be a number much bigger than 1. Right? Positive exponents are very big numbers, negative exponents are very small numbers. On top of that, we know that choice 2 is bad because this is not a single digit number. Right? You always want single digit numbers before your multiplication sign for correct scientific notation. So that's a big no-no. Right. And for our last practice problem of the day, how many joules are equivalent to 35 kilojoules? And again, I'm going to remind you, there are 1,000 joules in 1 kilojoule. Right, there's 1,000 whatevers in 1 kilo whatever every time, no matter what. So for this, if I want to go through and solve, I know that there are, right, I have a couple of different methods. I can say 35 kilojoules is equivalent to some number of joules. And I also know that 1 kilojoule is equal to 1,000 joules. I can make my ratio, I can make my proportion, and I can solve this by cross-multiplying. Solving by cross-multiplication is going to give me 35,000 joules. I could try it a different way. I can try it by saying I know that there are 35 kilojoules, and that's going to be equal to some number of joules. I know that kilojoules are 1,000 times bigger, so 3 decimal places bigger, so I should make this number 3 decimal places bigger. So from 35 I'm going to add 3 decimal places to make it 35,000 joules. Again, no matter how you slice it, you are going to end up with 35,000 joules as your answer. Right? Be very careful when you're looking at what you are converting, right? Where did you start and where did you end? Kilojoules are bigger than joules. And so you're going to have to make this number bigger to make it into joules. And with that, we're going to wrap up our first lesson. I'm going to ask everyone to jump over to our Google Meet, where if you have any more questions, comments, or concerns, we will take care of those and also our attendance. So I will see you there in a little bit.